This is from 2020 August Algebra Qualifying Exam, rings and fields, question 4. We have F being a finite field with characteristic P, super important. F. Cool. So we have the characteristic of F being P. We have this set of coordinates, so kind of F cross F, and we define Q to be from V into F by the map where our coordinate point AB goes to A squared plus B squared. And we're trying to prove that this map Q is onto. So that's the goal. That's going to be the point. So proof. So starting off, we have that F is a finite field and it has characteristic P. So writing out the degree of its extension over its prime subfield, we're going to get that it has an extension of some n. It's finite, that's the point. So this means that we have at least n, or we have n linearly independent basis vectors for F as a vector space with scalars from Fp. So then, for any element in F, you can say x is going to be equal to C1 B1 plus C2 B2 plus Cn Bn. And each of these bases, each of these scalars have P choices, which means you have P times itself n times, i.e. F has cardinality P to the n. And that's not immediately important, but I'm doing it now to get it out of the way. Okay, cool. So the way we're going to do this is we're going to define a set S to be all of these elements in F squared. All right, and then we're going to look at two elements in S, and we're going to pick 2 A comma B in F such that their squares are the same. And if this is the case, we can pull them across and then factor out A minus B, A plus B equaling 0. And because we're a field, that means we're an integral domain, so we don't have any zero divisors. And not zero. We're assuming they're non-zero elements, their squares are non-zero, which means these terms have to be 0. So our possible, this implies then that either A and B are equal or they're off by a sign. What does that mean? That means that not including 0, the size of S is at least P to the n minus 1, because we're not including 0 yet, divided by 2. And then for any x squared equaling 0, again, we're a field, so we're an integral domain. This automatically implies that x is 0. So the only number whose square is 0 has to be 0. So we add one more term there. So we get that the size of this set is P to the n plus 1 all over 2. Cool. And we're going to come back over here. So I have S, set of squares, all the elements, in F. We have that the cardinality of S is equal to P to the n plus 1 all over a half. And now, this is getting back to our map. We're going to let X be in F. And then we're going to define the set X minus S to be the set X minus A squared, such that a squared is an element of S. Cool. So then when we've done this, we can consider the cardinality of x minus s. Oops, greater than or equal to. But its cardinality doesn't change. And this 1 over 2, because we're just shifting the elements by some amount. All right? So then we have two sets, S, and we can intersect it with x minus s, the shifted version. This guy has a little over half of the elements in F. This guy has a little over half the elements in F. So by the pigeonhole principle, this cannot be empty. Pigeonhole principle. Which implies that there exists a b squared, or a b squared in S, such that, what is it? Oh yeah, x minus a squared equals b squared, which means that x is equal to a squared plus b squared. And so we just select those a squareds and b squareds for our map in Q. So then there exists, we'll do it here, exists a, b, and v with Q of a,